Hello everyone. Today we are going to discuss the most important point in this topic, that is inorganic reaction mechanism of this, what is SN1 and SN2 reactions for inert and labile complexes. For that purpose we must know what is, we know that is the SN1 means what? See here I will take the revision, SN1 and SN2. SN1 means what? That is the dissociative reaction, the reaction mechanism. Okay. And here SN2 means what here? That is a associative mechanism. Okay. For that purpose, we must know this. SN1 means dissociative reaction mechanism, SN2 means associative reaction mechanism. Okay. Now we are going to start this. That is here, according to a VBT, first point here, according to VBT and some experimental discussions, what here the two criteria will be found. What these two criteria? That is here, according to VBT and the experimental discussions, that is the complexes of the type, that is the D0, D1 and D2 and a D10 octahedral complexes are labile, D0, D1, D2 and D10 octahedral complexes are a labile one. Okay, that is they follow according to CFSE and VBT path a SN2 of this SN2 path. Okay, that means what? That is a ability to form. First is a, that is what? That is the 7-member complex, and with dissociation in second step here. What? First step is association step. In a second step of a dissociation, there is formation of a 6-member complex, that is 1A stable one. But this is occurs due to the d orbitals, which are the inner orbitals one here. Okay, but d orbitals are of inner orbitals of which kinds of? Two types. Here these are the T2G orbitals here. Here if we are considering the EG orbitals, that is inner orbitals are either singly filled or fully filled. Therefore, the octahedral complexes of the type D3, D4, D5 and D6 complexes are inert one. That is, they follow the reaction path as a SN1. Okay. What is the point going on? That is, here the first step is dissociation step, step 1, and in step 2, that is the association of a complex, that is a step 2. Here first step, there is formation of a reduction of a coordination number of a complex, that is from 6 to 5, and here again it is increased to 5 to 6. Okay, this is due to the either EG orbitals in the d orbitals are singly filled or fully filled. Now here in this SN1 reactions, okay, and SN2 reactions, here whatever may be the nucleophile is used, here nucleophile is the nucleus leaving. According to its nucleus leaving, it can also act as a Lewis base. Now we have to consider here either the D0, 1, 2 and 10 octahedral complexes are the labile one, and the D3, D4, D5, D6 complexes are the inert one. They can follow the path that is equal to SN1, and these complexes are followed the path as a SN2. For this purpose, we must know what is meant by inert and what is meant by a labile complexes in case of a thermodynamically and kinetically. See here, the point here that labile complexes are those in which replacement of a ligand by another ligand takes quickly or fastly. Okay, these are called as labile complexes. And what are the inert complexes here? The opposite definition. Inert complexes are those in which replacement of ligand of one ligand by other ligand takes place in slowly. Okay. Now got the definition here. What is meant by labile complexes? The complexes in which the replacement of a ligand by another ligand takes place as a quickly or fastly. They are called as a labile ligand. And the inert complexes are those in which the replacement of a one ligand by the another ligand takes place in which way? That is the slowly. Now we can consider here the thermodynamic approach of the ligands. See here. Approach. First point, if the ligand is thermodynamically stable, what happens here? Its formation constant it is equal to I. Okay, and also they are kinetically labile. Okay, now second approach of thermodynamics, that is if the ligand is thermodynamically unstable means what here? That is it has its formation constant, its formation or what? Its dissociation. Now here what happens here? That is if the ligand is a thermodynamically unstable, that is its formation or a dissociation constant having the low value That means they are kinetically inert complexes. Inert complexes. These are labile complexes. This is the trick to identify whether the complex is a stable or a unstable. What is the thing is thermodynamic approach. You have to just keep in mind, it is very important from the exam point of view, from the MCQ point of view. Okay, that is, if the ligand is thermodynamically stable one, its formation constant is equal to what? That is a high value. They are of a kinetically labile complexes. And if the ligand is a thermodynamically unstable one, here what happens? Its dissociation or formation constant, it is of a low value, and they are kinetically inert complexes. Okay. Now, for this, you have to consider such one example, that is FeH2O 6 3 plus having the formation constant, that is equal to what here? That is 1 1 here 1 2 1, that is kilojoule per mole, and of a CrH2O 6 3 plus is of 112 kilojoule per mole. Now out of these two complexes, these complexes are thermodynamically what? A stable one. Thermodynamically stable one. But as far as its inertness and labileness is considered, here this FeH2O H2O6 3 plus is more labile than that is the CrH2O 6 3 plus. What? That is the due to this dissociation constant one. What is this example? This example creates you to the mind, that is if the complex is a thermodynamically stable one or a unstable one, kinetically is labile or kinetically a inert one. Okay. Thus, we have discussed again the SN1 reactions. First of all, here we can discuss again the SN1 type of reactions. First one, SN1 reactions. Okay. Now, SN1 reactions means what? That is the unimolecular nucleophilic substitution reactions. Now we will consider its characteristics, not a associative, dissociative, likewise that. Okay. As far as this SN1 reaction, that is the unimolecular nucleophilic substitution reactions, here first, by considering its graphical representation, that is E by reaction progress here. This is the path. Okay. This is the activity complex, this is the interchange, this is the activation state 2, and here the products are. Okay. Now we are considering that is the high amount of energy, the high energy is needed for reactant to activated state first. Okay. Second, the low amount of energy is needed for the second activation energy, activated complex, not energy, complex to a product one. Got it? The high amount of energy is required from this reactant to the first step. Therefore, here this step is also called as, third point is that, here, as the high amount of energy is needed from reactant to activation state first. That is, the first step is nothing but the rate determining step. Second, it is a very slow process, slow step. Okay. Third, the rate of a reaction is directly proportional to concentration of mLn. Okay. Therefore, rate is equal to what? K into concentration of mLn here. And last point is, as the rate is dependent on the concentration of only one component, that is, the reaction is of a first order. Now, in order to define the mechanism pathway here, we have to keep in mind these all the conditions and all the characteristics. See the mechanism part here, that is the SN1 reactions mechanism. See here, first one, that is mechanism. You can draw here as Ml5 L X, that is the Ml5 and X. Cn is equal to what? 6 here. There are two paths here, as like this. Just you can concentrate on this path here. First path is what? That is the minus X here, and here also minus X here. What is the remaining one? Lm. Okay. Then what here? Ml5 here. Okay. Thus, okay, and here what? Ml okay, this geometry is what? That is Ml5, that is, it is what? Square pyramidal, and here Ml5, that is, it is what? A trigonal bipyramidal. Okay. Now, this is a trigonal one, that is the TBP, and here the square pyramidal. This is the square pyramidal. Okay. Now, like this, on this here, again, here plus Y. Okay. Here also a plus Y here. What happens here? That is Lm here Y okay, this is, that is Ml5 Y. Okay, 1 2 3 4. Okay, here 1 2 3 4, and here a 5. Okay, here also 1 2 3 4, here also a 5 here. That is here Ml5, that is 1 2 3 4 5. 1 2 3 4 5 here. Okay, thus this is of a coordination number is equal to 6 here. That is a octahedral. Okay, this is minus X. This is a slow step. Okay, this is also a slow step. Okay, RDS. Here also RDS, the determining step here. These are the intermediates. TBP, trigonal bipyramidal, and here SP is square pyramidal. Okay, this is the reaction mechanism for this. This is octahedral Ml5X. In the first step, that is called as a dissociation step here. Okay, in SN1 reaction mechanism, there is the formation of either trigonal, bipyramidal, or a square planar one here. Again, which is on a fast step. Fast step here also. Incoming ligand. This is called as a incoming ligand or also a nucleophile one, which attacks on this complex, and thus there is a formation of a stable octahedral complex of a Ml5Y. Okay, thus we have here explained here SN1 reaction mechanism in detail through a dissociative mechanism. In the next lecture we are going to discuss the second mechanism, that is called as the SN2 mechanism. Okay, thank you.